Okay, Chapter 7, Hypothesis Testing. So now we enter a new era. Government, business, and the hard and soft sciences all use and often abuse these tests of significance. It's all about answering the question, could these observations really have occurred by chance? So what this is really saying is how the government or media in particular kind of falsely make claims, kind of manipulating the laws of statistics. But we'll look at how hypothesis testing really should be done and kind of what the actual meaning is. So we begin with an example from the law, a composite of several cases argued in the South between 1960 and 1980, in which expert witnesses presented the case for racial bias in jury selection. So pure coincidence or critical likelihood. Panels of jurors are theoretically drawn at random from a list of eligible citizens. However, in southern states in the 50s and 60s, few African Americans were found on jury panels. So some defendants challenged the verdicts. On appeal, expert statistical witness gave this evidence. 50% of eligible citizens were African American. On an 80-person panel of potential jurors, only 4 were African Americans. Could this be the result of pure chance? For the sake of argument, suppose that the selection of potential jurors was random, then the number of African Americans on the 80-person panel would be the binomial random variable x with n, or sample size, equals 80 trials, and proportion equals 0.5, or 50%. So 80 Bernoulli trials, each with a proportion of half. Thus, the chances of getting a jury with only 4 African Americans is probability of x is less than or equal to 4, which works out to be about, well, 0.0000000014. Is that a small number or a big number? So this is a deductive probability argument. Since the probability is so small, the particular panel with only 4 black members is strong evidence against the hypothesis of random selection. To drive the point home, the statistician notes that this probability is less than the chances of getting 3 consecutive royal flushes in poker. So the judge rejects the hypothesis of random selection. If I was in that poker game, I started shooting after the second royal flush, and orders his own remarks stricken from the record. So how do we formulate a hypothesis? First, we need H0 or H null or H naught. That's our null hypothesis, is usually that the observations are the result of pure chance. The second hypothesis is going to be HA for the alternative hypothesis. Sometimes they use H1, is that there is a real effect, that the observations are the result of this real effect plus chance variation. So in the court case, the null hypothesis says the jury was randomly chosen from the whole population. African Americans have probability P equals 0.50 of being chosen. The alternative hypothesis says that African Americans are less likely than their proportion in their population to be selected for a jury. So P is less than 0.50. Step 2. The test statistic. Identify a statistic that will assess the evidence against the null hypothesis. In the court case, the test statistic is the binomial random variable x with p equals 0.50 and n equals 80. So it's like flipping a coin 80 times. Step 3, p-value, a probability statement which answers the question, if the null hypothesis were true, then what is the probability of absorbing a test statistic at least as extreme as the one we observed? The smaller the p-value, the stronger the evidence against the null hypothesis. So in the example, the p-value was the probability of x is less than or equal to 4, given that p equals 0.5 and n equals 80. We got 1.4 times 10 to the negative 18, so it's an incredibly small number. We computed this p-value the modern way using a statistical software package. So, step 4, compare the p-value to a fixed significance level alpha. So we talked about that last week. Alpha acts as a cutoff point below which we agree that an effect is statistically significant. That is, if p-value is less than or equal to alpha, We rule out the null hypothesis and agree that something else is going on. In the jury case, the statistician took alpha to be 3.6 times 10 to the negative 18. The chances of being dealt 3 royal flushes in a row, a p-value even a judge can understand. In scientific work, a fixed alpha level of 0.05 or 0.01 is often used. These fixed levels are a holdover artifact from the pre-computer era, when we had to refer to tables which were printed only for selected critical values. Still, many scientific journals continue to publish results only when the p-value is less than 0.05. Even though 1 time out of 20 results with a significance level of p is less than 0.05 are false. So kind of have this norm that's still there and that we still follow even though we really should have found something better by now. In legal proceedings, the standard is more flexible. So our first example, we want to set up a hypothesis test. So a media research company conducted an online survey of adults in a certain country to determine their favorite sport. A friend believes professional football, with revenue of about $8 billion per year, is the favorite sport of more than 50% of adults in the country. Specify the null and alternative hypothesis for testing this belief. Be sure to identify the parameter of interest, complete the null and alternative hypothesis below. So, in this case, what we're interested in is this 50% number. So I don't have a tab for this one, but we're interested in creating an HO, or the null hypothesis. And we know that it was 50%, so the null would be that the proportion is equal to 0.50 or 50%. The alternative, or HA, would be that the proportion is greater than 50%, which would indicate more people would watch the sport than not. That's how we would set up a very simple hypothesis test. Okay, so that's how we set up the beginnings of a hypothesis test. So, large sample significance test for proportions. The jury example was a special case of a general problem. The null hypothesis had the form P equals P naught, where P naught was some probability, in this case 0.5. Now let's look at such problems generally. Let's test the hypothesis P equals P naught. As usual, we imagine we have a big population. We observe a large sample, and we find that some characteristic occurs with probability P hat. Based on this observation, we want to know if the true population probability is, for instance, larger than some other value P0, P naught. For example, Senator Astute, having found a P hat of 0.55, would like to know that P is greater than 0.5, a winning majority. Step 1. So the null hypothesis is that P is equal to this P naught value. The alternative hypothesis depends on the direction of the effect we are looking for. In Senator Astute's case, we want P to be greater than P naught, which would indicate a winning majority in an election. But in other cases, the alternative hypothesis might be P less than P0, or P does not equal P naught. For example, if the jury selection example, the alternative hypothesis was P is less than 0.5. So there was less than 50% African American jurors. And at other times, we're interested in knowing that P is different from some value. So P naught, for instance, in testing for a fair coin, we have an alternative hypothesis of P does not equal 0.5. But we have no a priori opinion about whether heads or tails will come up more often. Step 2, a test statistic. So for large samples, we of course can use the normal curve and get a z-score. So, and we should know how to calculate a z-score. So it's the same formula that we talked about last week, which measures how far P deviates from P0 under the null hypothesis. The z observation has the standard normal distribution. So you can use the z-table, or you can use the calculator that I created last week. Step 3, the p-value depends on which alternate hypothesis is relevant. So a right-handed one-tailed test, so HA, or the alternative hypothesis, p greater than p0, uses p-value probability of z is greater than our z observed. So this comes back to that 1.96 for talking about, an alpha of 0.05, and I don't know, is our t value that we calculated here, or z value, going to give us a p-value less than 0.05, and that would be in this right tail here. So our left-handed test would be the other way. We would be looking for a very low negative value, but same idea. You'd have negative 1.96 if we're looking at an alpha of 0.05, and so we'd want a p-value of less than that value, and that would be in the left-hand side. But when you're doing one-tailed tests, the process is pretty similar. If we're doing a two-tailed test, or two-sided test, this is when we had to divide alpha by 2. We talked about that last week, but when you see that the alternative hypothesis has a not equal to sign, and that's when we're going to have to use that particular test. So it uses the p-value of the probability of the absolute value of z is greater than the observed absolute value. But we know that we take whatever our alpha value and we divide it by 2, so we have smaller sections in both tails. This is actually the more likely used hypothesis test, because in general we don't know the direction of the hypothesis we're trying to test, and since this would give us smaller regions, statisticians are more likely to believe your results under a two-sided test. In the case of Senator Astute, the hypotheses are that we're going to test is the null hypothesis is p equals 0.5, and the alternative hypothesis is p greater than 0.5. So his test statistic calculated out, using this formula, we get a z-score of 3.16. The p-value is 3.16. We calculate that out, and we get a p-value of 0.0008, which is pretty small from the normal table. So Astute, being fairly conservative, takes a significance level of alpha of 0.01 and observes that 0.0008 is less than 0.01. So you reject the null. The senator thus rejects the null hypothesis, and he and his backers now feel certain he's in the lead. Sample 2. Suppose a random sample of 100 observations from a binomial population gives a value of p hat equals 0.73, and researchers wish to test the null hypothesis that the population parameter p is equal to 0.8 against the alternative hypothesis that p is less than 0.8. So let's go to 7.2. So noting that p equals 0.73, does the value of p appear to contradict the null hypothesis? So the value of p appears to contradict the null hypothesis because it satisfies the alternative hypothesis and not very close to 0.8. So we can calculate in Excel and get the test statistic 0.75. So we had a sample size of 100. We had an estimate of p hat 0.73. We have our null hypothesis of 0.8. Our alternative hypothesis that p is less than 0.8. We're interested in an alpha of 0.05. So we put that into our formula here. It calculates out our z-score of negative 1.75. Then I use this formula here. So the normal curve distribution, it takes this z-value and goes back and pulls the p-value, and then I have it round to 2 decimal places. So we get a p-value of 0.04. So what is the critical region? This is a one-tailed test at 0.05, so the critical region is negative 1.65. So we're looking for a number further away from 0, so negative 1.75 is further away. So just from the critical value, we know that we can reject the null, but you can take it one step further to determine the proper conclusion. we reject the null. There is sufficient evidence to indicate the true population proportion is less than 0.8. So we can find the p-value using that score, and we know that 0.04 is less than 0.05. Thus, we can reject the null hypothesis. So that's the first calculator for calculating out a very simple one-tailed hypothesis test. Right, large sample test for the population mean. Here is how a significance test might be used in inspection sampling, an important industrial application. So, feels light, man. Heavy, man. Anyhow, New Age Granola Inc. claims that the average weight of its cereal boxes is at least 16 ounces. The Genuine Grocery Corporation will send back a shipment if the average weight is any less. But of course, Genuine Grocery has no intention of weighing every box in a shipment. They're going to use statistics. So first they choose their hypothesis. So 1 pound is 16 ounces. So they're saying that the null hypothesis that the mean is equal to 16 ounces. And the alternative is that the mean does not equal 16 ounces. And in that case, if it doesn't, they're going to send back the box of cereal, and these people are not going to make any money. So rejecting the null hypothesis means refusing the granola rate. Next, they choose a test statistic. By now, it should be pretty much a knee-jerk reaction. Know that the sample spread from the mean is the difference of sample point estimator from the true population mean divided by the standard error of that particular mean. So where S is the sample standard deviation under the null hypothesis, this approximates a standard normal when the sample is large by the central limit theorem we talked about last week. Skipping over step 3 for a moment, they set a significance level being a bunch of dropped out science majors. The grocers think alpha equals 0.05, sounds about right. It's a pretty typical norm. So just then a boxcar loaded with 10,000 boxes of granola arrives at the door. They pull out a sample, random sample of course, of 49 boxes and weigh each one and determine the sample's summary statistics. So the X-bar or sample mean is 15.90, which is less than the 16 ounces, right? So, but is that statistically significant? So we have a standard error or standard deviation of 0.35 ounces. So a little light, but is it significant? We plug those values into the test statistic to find their z-score of -2. Now they compute the p-value. Probability of z less than -2 is 0.0227. This being less than 0.05 significance level, Genuine Grocery rejects the null hypothesis and sends the shipment back because the boxes of cereal in general were too light. So they rejected the null. What happened? The guy ate too much of the cereal. Anyhow, so example 3. So consider the test H naught, the mean equals 74 versus the alternative hypothesis that the mean is greater than 74, using a large sample size of n equals 375 and assume a standard deviation of 24. So find the value of the test statistic if x equals 76.3. What is the p-value for this x-bar? And find the rejection region for alpha 0.05. So let's take a look at that. So describe the sampling distribution of x-bar. Since the sample size is sufficiently large, sampling distribution is approximately normal. So we were given our hypothesis test that the mean was 74 and that our alternative hypothesis was greater than 74. We have n, sample size of 375. Our sigma, our standard deviation, is 24. The sample mean that we are testing is 76.3, our x-bar. So we use this formula to calculate out our z-value. Then we round that to get the opposite side of our alpha. So we get an alpha value of 0.032. So Z alpha is less than 0.05 because we were testing on 0.05. So we can reject the null. If we're going to look at it with critical value, we have a critical value of 1.645. So this is a one-tailed test. So that is the equivalent to 0.05 for a one-tailed test. We have a table that we looked at last chapter or last week that will help you pull that number if you didn't know what the value was. And of course, 1.85 is greater than 1.645, and in both cases, we reject the null hypothesis. So there's sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean is greater than 74. Small sample test for the mean population. So are you sure for this? So we return to Chameleon Motors and its 10-mile-per-hour crash test that we talked about last week. So the righteous insurance company will insure an auto only if the mean repair cost after a 10-mile-per-hour collision is less than $1,000. The company uses standard alpha equals 0.05 as the significance level. So return to Chameleon Motors and its 10-mile-per-hour crash test. The righteous insurance company will insure an auto only if the mean repair cost after a 10-mile-per-hour collision is less than 1,000. The company uses a standard alpha equals 0.05 as its significance level. So our null hypothesis, H naught, is that the mean, mu, is greater than or equal to 1,000. The mean cost is too high. The alternative hypothesis is that the mean is less than 1,000. The mean cost is okay. So the test statistic is the t-distribution because our sample size is below 30, and thus we need to use a t-test instead of a z-score. So same basic way you calculate it out, we just pull the t-statistic from a different table. So t with 4 degrees of freedom, we want our observed t-value to lie to the left of that negative t.05 value. Because low x bar is desirable, the x bar minus the population mean should be negative to support our alternative hypothesis. So this is from the t table of critical t-values. We see that t.05 equals t2.13. So we decide to reject the null if the t observed is less than or equal to a negative t.05. So we have negative 2.13. And from a previous chapter, we have x bar equals 540, and the s equals our standard deviation is 299. For a small 5-car sample, we find that t observed is negative 3.44, which is more negative than negative 2.13, right? So we should be able to reject the null hypothesis that the mean value for collisions is greater than or equal to 1,000. So car passes the test, the null hypothesis is rejected, and the insurance policy is issued. So this is an example of acceptance sampling. The null hypothesis is that repair costs are unacceptable and the motor company is assumed guilty until it presents sufficient evidence of its innocence. An example, that its product is within specs. Okay, so next example is to calculate p-values or type 1 errors for these sets of values. So pull this up. So for a one-tailed test to the right, t greater than 1.440, we have 1.44. We have 6 degrees of freedom. So remember, to get degrees of freedom, it's 1 minus the sample size. So if n was 7, it would be 7 minus 1 equals 6. We're interested in 90% confidence. And we get an alpha of 0.1. So to calculate these out, we use the t.dist or the t-distribution. It uses our critical value or t-statistic and the degrees of freedom. And then I have it rounding to, I think, to 3 decimals, but for the alpha. Yeah. So we'll be looking for a particular alpha or p-value or significance level, and that's where this comes out. All right, so here's kind of a table for the different tests we just went over. So for a normal distribution, our sample size greater than 30, and we know what the standard deviation is, we use population mean and a z-score. However, if we have less than sample size of 30 and we don't know the standard deviation, then we want to use the t-distribution. And for proportions, we have a special rule that you need to remember. The sample size times the proportion needs to be greater than 10 for either side usually. So, and in 1 minus p hat should be greater than 10. So if you have 30% of p hat of interest, then you need to make sure that you also have a sample size that of for the 70%, the other side or the complement of that proportion, and both need to be greater than 10 in order for you to run a z-test. So, decision theory. We can think of hypothesis testing and significant tests in terms of a household smoke detector. If you have one of these where you live, you probably noticed how it tends to go off every time you make the toast too dark. This is what is called a type 1 error, an alarm without a fire. So conversely, a type 2 error is a fire without an alarm. Every cook knows how to avoid a type 1 error. Just remove the batteries, unfortunately. This increases the incidence of a type 2 error. Similarly, reducing the chances of type 2 error, for example, by making the alarm hypersensitive, can increase the number of false alarms. So we can summarize this in a 2x2 decision table. So if there's no alarm and no fire, then there's no error. If there's no alarm and there is a fire, that's a type 2 error. That would be really bad. So if there's an alarm and no fire, then that would be type 1. So that would be like a false alarm, right? Not too bad, just an irritation. And then if there's an alarm and a fire, well then that's no error because the alarm did what it was supposed to. Now think of the null hypothesis as the condition of no fire, while the alternative hypothesis is that a fire is burning. The alarm corresponds to the rejection of the null hypothesis. So if we accept the null and the null is correct, then that's not an error. If we accept the null but the alternative was correct, that's a type 2 error. If we reject the null but the null was true, then that's a type 1 error. But if we reject the null and the alternative was true, then that's no error. All the significance tests we did earlier in this chapter emphasize the probability of committing a type 1 error. An example, the probability of our observations occurring if null or the null hypothesis was true. We demanded that the probability of rejecting the null given the null was equal to the probability of a type 1 error given the null was equal to alpha. So 1 minus alpha measures our confidence that any alarm bells we hear are genuine. So high confidence means rarely setting off false alarms. So that's kind of the 95% confident with the alpha 0.05 that I talked about last week. Sometimes what we really want to know is the chance of making a type 2 error. In other words, how sensitive is our alarm system? And the alternative hypothesis is true. So an environmental example. In the past, factories discharging chemicals into waterways were required to show that the discharge had no effect on the downstream wildlife. That's the null. The polluter could continue as long as the null hypothesis was not rejected at the 0.05 significance level. In the past, factories discharging chemicals into waterways were required to show that the discharge had no effect on the downstream wildlife. That's the null. The polluter could continue as long as the null hypothesis was not rejected at the 0.05 significance level. So a polluter, suspecting that he was in violation of EPA standards would devise an ineffective pollution monitoring program. Well, we'll interview a few ducks. Polluter is delighted since, like our smoke alarm without a battery, his test was little or no chance of setting off an alarm. Duck responded enthusiastically. But let's formalize this idea to describe the probability of a type 2 error. We break out another Greek letter beta, which is the Greek letter B, beta. So the probability of accepting the null given the alternative is equal to the probability of a type 2 error given the alternative. So the power of a test is defined as 1 minus beta. So it's the probability of rejecting the null given the alternative hypothesis. It's called power. You'll be happy to know that the environmental regulators have moved in the direction of requiring pollution monitoring programs to show that they have a high probability of detecting serious pollution events. The required power analysis often reveals hidden flaws in the monitoring program. One way to visualize the effects of a test's power is by graphing the probability of rejecting the null against the actual state of the system. In the case of the smoke alarm, the probability climbs toward 1 as the smoke gets thicker. For the EPA water quality example, the horizontal axis is the true concentration of pollutant in the water. Here are the power curves for 3 monitoring programs. The Save Every Last Guppy cost $5 million, the Golden Mean cost $500,000, and Don't Rock the Boat also cost $500,000, but they put on a good show. The higher the test power, the steeper the curve. All right, Chapter 8, Inferences on 2 samples. Does a particular pesticide increase the yield of corn per acre? Do men and women in the same occupation have different salaries? In this chapter, we'll use our meat and potatoes methods and some new recipes that will help us answer the following questions. Does taking aspirin regularly reduce the risk of a heart attack? A common ingredient in these questions is this. They can be answered by comparing 2 independent random samples, one from each of the 2 populations, the use of pesticides and no pesticides. And at the end of the chapter, we'll look at different ways to compare 2 means that doesn't involve taking 2 simple random samples. So comparing the means of 2 populations. Suppose we wanted to compare the average salary of male and female employees in the same job at some company. Population 1 is the women and population 2 is the men. Population 1 has a mean salary of mu1 and standard deviation sigma 1. And population 2 has mean mu2 and standard deviation sigma 2. As you can see that in the graph, there's a skewness for the population of the women and the lesser. The random sample of size n1 from group 1 and n2 from group 2 gives a sample means of x1 and x2, and standard deviations s1 and s2. Respectively, the estimate of the difference of the means is the difference of the means of the samples, x bar 1 minus x bar 2. How good an estimator is x bar 1 minus x bar 2? For large sample sizes, it's approximately normal by the central limit theorem, and its standard error is calculated out based on this formula. So the variances add, since samples are independent, now we can proceed directly to confidence intervals. For large sample sizes, the 1 minus alpha is equal to 100%. Confidence interval for the difference between means is basically just take the difference of the means and the standard errors and find the z-value divided by alpha divided by 2, and you come up with the confidence interval. I'll do this in a second. Hypothesis testing. We assess the null hypothesis that the 2 population means are equal. So the null is that the 2 means are equal, right? So the test statistic is to find the z-value that corresponds to the differences of those 2 values. The p-values work in the usual way. So So suppose the first sample is selected from a population with mean U1 equals 135 and variance sigma squared equals 2500. Then what range should the sample mean vary about 95% of the time and repeated samples of 100 measurements from this distribution? That is, construct an interval extending 2 standard deviations of x1 on each side of mu1. So we were given, let's see, that our mu1, or our population mean 1, was 135. We were given our variance, sigma squared, for 1. So we have to take the square root of that to get the standard deviation. We are interested in 0.95 or 95% confidence. We know that for z alpha 2 of 0.95 from the table, that's 1.96, one of the numbers you should memorize. And we had a sample size of 100. Okay, so now suppose the second sample is selected from a population with mean U1 equals 135 and variance is 14,400. So within what range should the sample mean vary? About 95% of the time in repeated samples of 100 measurements from this distribution. That is, construct an interval extending 2 standard deviations of x1 on each side of mean. So that gives us our confidence interval there. We put in their values here. So we had a mean of 135 again, but this time our variance was a lot bigger. So we had a variance of 14,400. So to get the standard deviation, we take the square root. We're interested in 95% confidence interval. So we know that 1.96 is the critical value that we need and a sample size of 100. So we calculate out our confidence, and then we get our confidence interval here. So we can see, because the variance was so much bigger in the second population, that our confidence interval is wider in the second sample than it is in the first sample. So now consider the difference between those two sample means, x1 and x2. What are the mean and standard deviation of the sampling distribution? Okay. So what we're interested in is that there is no difference in the mean, right? So no difference there, but there is a difference in the standard deviation. And to find that, we had to take, the difference in those values, and we have to compensate for the sample size. So we get 0 and 13. And finally, within what range should the difference in sample means vary? About 95% of the time, repeated independent samples of 100 measurements each from the two populations. So we get between negative 26 and 26. So it's plus or minus this value. So calculating that all out. So this is the interval that we're interested in. All right, so another example. In order to compare the means of two populations, independent random samples of 385 observations are selected from each population, with the results found in the table. So use a 95% confidence interval to estimate the difference between the population means mu1 minus mu2. Interpret the confidence interval. Test the null hypothesis that the difference between those two means is equal to 0, versus the alternative hypothesis that the difference in those means does not equal 0, given the significance of the level, and interpret results to use alpha equals 0.05. So our first sample, our sample mean is 5,314 with a standard deviation of 157. And our second sample is X bar at sample mean of the group 2 is 5,279 with a standard deviation of 199. So yeah, our next one. So we have this long formula to use. We have our two sample means and our standard deviations, and we have our difference in those means. So the second part, based on the same information, what is the hypothesis difference? Was 21 instead of 0? So we'll come to that. So we know that we had 385 observations. You know the variance calculated out. So using these, we can get and this formula here that I've put into the spreadsheet, we can calculate out our interval. We have 9.7 to 60.3. So we use this to calculate out our z-score. And we get 2.71. So based on a p-value of a two-tailed test, that gives us a p-value of 0.007, which is less than 0.05. So second part of that question was, what if it was 21 instead of 0? So our null hypothesis would be that mu1 minus mu2 equals 21, and the alternative would be mu1 minus mu2 does not equal 21, basically. So based on that, so using the same formulas, except now we have 35 from 21. That's going to give us a slightly different value. We get a z-score of 0.0 or 1.08, and plugging that in, we get a p-value of 0.278. So in this case, we would not reject the null hypothesis if the hypothesized mean was, or difference in the mean was 21 instead of 0. Right. So comparing success rates or failure rates for two populations. We begin with an experiment, part of a Harvard study that sought to decide the effectiveness of aspirin in reducing heart attacks. As in most clinical trials, the chances that any one individual gets the disease, in this case, heart attack, is very small in any given year. We want answers quickly. So what do? Can't take 20,000 aspirin. A simple but expensive solution is to test a large number of individuals in a short time. In this study, 22,071 subjects, all volunteer doctors, were randomly assigned to two groups, aspirin, not, and aspirin. So group 1 took a placebo, a pill identical to aspirin but contains no aspirin, and group 2 received 1 aspirin a day. Over a period averaging nearly 5 years, the investigators recorded the responses. Heart attack or no heart attack. The result, and the numbers that follow, we have combined fatal and non-fatal heart attacks. So, in the placebo case, we had 239 attacks and 10,795 attacks. In the aspirin group, we had 139 attacks and 10,898 non-attacks. Sample sizes were roughly equal, 11,034 to 11,037. We find the proportion of the attack rate, so p hat 1 is 0.0217 and p hat 2 is 0.0126. So the observed difference in success rate is p hat 1 minus p hat 2 equals 0.0091. Sounds like it's very small until you look at the relative risk. So the p hat 1 divided by p hat 2 comes up to 1.72. So members of the placebo group were 1.7 times more likely to suffer a heart attack than those in the aspirin group. So this study was stopped early because of its positive outcome. It would have been unwise and impractical to deny the results to the group taking the placebo. The model, the placebo and aspirin group observations are independent. Samples from two binomial populations for consistency refer to a heart attack as a success. Placebo, population 1, chance of success equals P1. Aspirin population 2, chance of success equals P2. So the objective is to estimate the true difference of those two proportions. For each population, actually large samples of the general population, we have the familiar random variables x1 and x2. So x1 is the number of successes in population 1, and x2 is the number of successes in population 2. P hat 1 is the proportion of the sample mean to the total population 1, and P hat 2 is the x2 divided by the population or sample size of the second sample or population. And an estimator of the difference between those rates would be P hat 1 minus P hat 2. Sampling distribution for P hat 1 minus P hat 2. So for large samples, difference in these two proportions is approximately normally distributed. Which as the case of only one sample, we can make the usual z transform to get a standard normal random variable. So we get a z-score based on this formula. How do we find that standard deviation in the denominator? So, since the two samples are independent, so are the random variables, p hat 1 and p hat 2, and the two variables add. So we use this formula. And now, knowing the distribution of the test statistics, we can proceed to estimate confidence intervals and test the hypothesis that aspirin reduces heart attacks. So, confidence intervals for difference in proportions, very similar to what they were for one proportion. We just take the difference of those two proportions and the difference in their standard errors, and we multiply it by our critical value, z alpha 2, probably 1.96 for a 95% confidence interval, and then we add and subtract it to get the two ends of our confidence interval. The variances of p hat 1 and p hat 2 adds the standard error. So it's basically the same formula like before, so we're looking at the differences of them. So in the aspirin theory, standard error was 0.00175. So to get the 95% confidence interval for the aspirin study, we just plug in the observed values. And we get 0.0091 plus or minus 0.0034. So we're at least 95% confident that the difference in heart attack rates is between 0.0057 and 0.0125. Definitely a positive number, and we are now at least 95% confident that aspirin really does lower heart attacks or heart attack rates. So, hypothesis testing. The formal hypothesis testing question is, aspirin had no effect, what is the probability that the result occurred by chance? So the null hypothesis is that the aspirin had no effect. So the proportion of P1 is equal to that of the proportion of P2. So the alternative is that aspirin does reduce the heart attack rate, thus P1 is greater than P2. So now we need a test statistic or the normal distribution when the null is true. So when the null hypothesis is true, the standard error depends only on this pooled estimate. So this is a pooled test. And we can write that test statistic here. So the difference in the proportions divided by the standard error of the proportions. And to get the standard error, we have the square root of p hat times 1 minus p hat, and then our sample normalization. So now note that under h dot, the two proportions are the same. So let's pull all the data to get the proportion of heart attacks in both samples. So numerator would ordinarily be, p hat 1 minus p hat 2 minus p1 minus p2, but the null assumes that that difference is 0, so we can just drop that from it. So it makes it a little easier. So for the aspirin study, we find 378 divided by 22,071 is 0.0175, and our z observed based on that number is 5.20. So z observed is more than 5 standard deviations from 0, a strong positive effect. So using a table or computer, we find that the p-value is 0.000001, which is super small. The null hypothesis for true, the probability of observing an effect this large as 1 in 10 million. So very strong evidence against the null hypothesis. So minimum sample size to test a hypothesis proportion. Basically, you should use that both proportions you have sample size greater than 15. Let's see if I have So let's look at a couple of examples. Determine if n1 and n2 are both large enough. So we have n1 equals 14 and n2 equals 11. So we need to multiply those out by their proportions. Have a separate sheet for that one, but pretty easy to do. We multiply n1, p1, n2, p2. So we have 14, 2, 11, 0.58. So these need to be this. So based on this, those values are too small. Okay. The next example, construct a 90% confidence interval for P1 minus P2. So if we have a sample size 400 and proportion of 0.68, and the second sample size is 400 with a proportion of 0.56. So we have our values. So sample size 400, our P1 was 0.68, Q1 is 1 minus P1. We do the same thing for our second proportion. So the sample size was 400, P2 was 56 or 0.56. Thus, the complement to that is 1 minus 0.56, which gives us 0.44. We're looking at a 90% confidence interval, so our Z alpha 2 is going to be 1.645. We have this really long formula here that we need to calculate out. I've also given you a confidence interval for Z alpha 2, so you can see if it was 95%, you'd use 1.6 or 96. If it was 99%, then you'd use 2.576. But we're interested in 90% confidence intervals, so you use 1.645. So we're looking at the difference in those two proportions. Then we're going to plug into all this formula, and we get 0.05627 based on Z alpha 2 times that. Then we're going to add that to our difference. So our difference was 0.12, and we're going to take that confidence, or basically this part of the formula, and add and subtract it to get our interval. So we'll get a confidence interval, or 90% confidence interval, of between 0.064 and 0.176. Example 5, a random sample of size equals n1. Our sample size is 60 and the second sample size is 70 were drawn from two populations. Samples yielded a proportion P1 equals 0.5 and P2 equals 0.3. So test the null hypothesis that the difference in those proportions is 0.1 against the alternative hypothesis that the difference in those proportions is greater than 0.1 using alpha equals 0.01. Okay, so we had our two sample sizes of 60 and 70. We had our first proportion was 50%, and our second proportion was 0.3 or 30%. We got our complements for Q, and we were interested in alpha of 0.01, or a 99% confidence. So our difference between the, or what we're testing is that the null hypothesis is 0.1, but the difference in those two proportions is 0.1. So we have our formula from here that we calculate out. We've set up some formulas, and we get z-score of 1.18. I left that is unrounded because in order to use it in the formula and get the correct answer, you had to not round, but so 1.18, but the not rounded version is here. We can use that in the p-value, and we get 0.2375, which is significantly greater than 0.01. So thus, we would have to not reject the null hypothesis or accept the null hypothesis. Okay, so I think that's all the examples I have for chapter 7 and 8.